Hello, these are the solutions to activity 3. How many neutrons are present in a phosphorus 32 atom? So this information here is the mass number. We have to look at a periodic table to determine the atomic number of phosphorus. Phosphorus is atomic number 15, so 32 minus 15 is the number of neutrons, so that'll be 17. So 17 neutrons. So remember again, the mass number is the sum of the protons and the neutrons, because they're the particles that carry most of the mass in our atom. How many protons and electrons does a sulfide ion contain? Sulfide is specifically S2-. It's the common ion of sulfur. Sulfur is closest to a noble gas count by adding 2 electrons, and so sulfur is element number 16. So we get 16 protons, 18 electrons. Number 3, silver exists naturally as 2 isotopes. We have 2 given atomic weights. What is the abundance of the lighter isotope? This problem here is a little bit tricky to maybe understand, but the idea of average atomic weight is that it's the sum of the fraction of a given isotope times the atomic weight of that given isotope, and we're summing these up over all possible isotopes. So for the case of silver, what we need to do is write this equation that it would be the fraction of the lighter times the atomic weight of the lighter, and then plus the fraction of the heavier times the atomic weight of the heavier isotope. So let's write those out here. So our average atomic weight So again, the fraction of that lighter isotope times its mass, plus the fraction of the heavier isotope times the atomic weight of the heavier isotope. Now there's 2 keys here. One of the keys is that the fraction of the lighter plus the heavier, because there's only 2 possible isotopes for this atom, that these have to sum up to 1. And then the second thing is that the actual sum, the average atomic weight, is given on the periodic table. For silver, that's 107.8682. Okay, so if what we want to find is the abundance of the lighter isotope, that's this value here, what we want to do is solve for the fraction of the heavier isotope, how it's equal to 1 minus the fraction of the lighter. So we can sub this in here. And then we can solve using algebra for the fraction of the lighter isotope. Now the only peculiar thing is this becomes a little bit of a long problem of algebra, where what we want to do is start filling in some of our data. Fraction of our lighter, the atomic weight of the lighter is 106.9051 AMU, and then plus 1 times the atomic weight of the heavier, so that's going to be plus 108.9047 AMU, and then going to be minus the fraction of the lighter times 108.9047. That this is all equal to 107.8682. Now, one thing we might do is just try to take a quick look at, the average is 107.9, the fraction of the lighter is 106.9, fraction of the heavier 108.9. So we're somewhere around 50%. Unfortunately, all the choices are around 50%. If some of these choices were not anywhere close to 50%, we could probably roll them out. So we have to kind of go about solving this problem here. So how do we solve this? Well, we just have to subtract 108.9047 from both sides. So let's do that subtraction here. So I'll take 107.8682 and I'll subtract 108.9047. So just subtracting that from both sides leads to this being negative 1.0365. And then what I might do is to imagine this is 106 times x and this is minus 109 times x or whatever. And so I just need to take 106.9051 and subtract 108.9047. That gives me negative 1.9996 times the fraction of the lighter isotope, and that's equal to negative 1.065. So I subtracted this from both sides. To get the negative 1.065, and then I'm just doing my algebra here to combine those values to negative 1.996. So now I take negative 1.0365 and divide it by negative 1.9996, and that gives me 51.80. Well, it gives me a fraction, 0.518, and then times 100%. Gets me 51.8%. Okay, so this problem here really just comes down to knowing that the average atomic weights are listed on the periodic table. So I needed to grab that value for silver to help me out on this problem. And that when we have two isotopes for a given atom, that their sum adds up to 100%. And so that allows me to solve for the fraction of the lighter isotope here using algebra. So tricky problem. Probably the hardest type problem you would ever see is something that looks like this one here. Other problems are just giving you some kind of data, trying to make this type of relationship and then solve a problem off of it. So there's a lot of problem solving skills and strategies in a problem like this that you might be able to appreciate that we could have given instead we could have given you one of the fractions of the one, then by default you know the fraction of the other. Then we could give you the average atomic weight of one of them and you can solve for the other. So we could give you bits and pieces of information you can use that to solve the remaining information. Let's look at some naming questions here. So we have calcium carbonate, or calcium sulfate, calcium sulfite. So how do we name this thing? So calcium 2 plus is calcium ion, SO3 2 minus is derived off of SO4 2 minus. This is sulfate, so this would be sulfite. So we're just memorizing sulfate, so this has to be calcium sulfite. So the next molecule is iron phosphate, but which iron? What's the charge of iron here? So if iron's a 2 plus, it gives me a total 6 plus for my cations. That's going to be the right charge because phosphate is a 3 minus ion. I have a minus 6 plus 6. Compound should be charge neutral. And so what we see here is that this is iron 2 phosphate. So the charge of iron is 2 plus. That's why we call it iron 2. And then phosphate. And so phosphate is PO4 3 minus. So that's why we have this connection of 3 irons, 2 pluses, and then 2 phosphates in this formula. And so the right answer here would be iron 2 phosphate. Now, what would iron 2 phosphite look like? Well, phosphite would just be the PO3 3 minus. So Fe2 PO3 3 would be iron phosphite. And then iron 3 phosphate and phosphite would have the iron 3 plus ion. And so it would be Fe3 plus. So those would just pair up with 1 PO4 3 minus. So a formula like Fe PO4 would be iron 3 phosphate. What is the formula of chromium 6 oxide? Well, chromium, see our and then 6 plus. And then oxide is O with a 2 minus charge. And so we're going to have 3 oxide ions here. So CrO3 will be the formula of chromium oxide, chromium 6 oxide. Not that one. Sorry, found the wrong one. The answer D. So it's important to think that the chromium 6 doesn't have to do with how many chromiums there are, doesn't have to do with how many oxides there are. It specifically has to do with the charge of chromium. And then you balance out the number of oxides based on the charge of 6 plus, and then the charge of oxide being a 2 minus. What's phosphoric acid? Ic acids are derived off of 8 ending ions. If you see an acid that's an OUS acid, these are derived off of ions that end in ITE. You see a hydro out in front of the name of the acid, then it would come off or be derived off of our simple ide ions. So real quick would be HCl is hydrochloric acid, so hydrochloric acid. HClO3 would be chloric acid, so this would not have the hydro, so this is just chloric acid. HClO4 would be perchloric acid. HClO2 would be chlorous acid, because this is chlorite. ClO2 minus is chlorite. Hydrogen in front would be chlorous acid. So phosphoric acid is derived off of phosphate, so that'd be derived off of PO4 3 minus. So this will be H3PO4. Write and balance the combustion reaction of butane. So combustion reactions where you have a hydrocarbon. So this will be C4H10 is butane. How do I know that's butane? Well, methane is the C4, the C1, H4. So this is methane. And then ethane just replaces this hydrogen with another carbon, adds hydrogens here, and then propane adds another carbon, and then butane is 4 total carbons. And so then the proper count of hydrogens is that the ends have CH3s, and then CH2s in the middle, so CH3, CH2, CH2, CH3, and that gives us a total of 3 plus 2 plus 2 plus 3 is 10. So this thing here reacts with oxygen. Oxygen's a gas. Butane, you might think of this in a lighter as liquid form. It's actually under pressure to liquefy it. At room temperature, I think it would be a gas. But you don't have to predict physical states of too many things here. But O2, we know that's a gas at room temperature, and that this is going to react with a flame to form CO2 and water. And then we just have to balance this out. And so then we'd have 4 CO2s being formed. We'd have 5 waters. This is going to lead to a fraction for O2. So right now this would lead to a fraction because we'd have 8 plus 5. So we need 13 halves O2. Generally, you don't want a fraction in your balanced reaction. So we can double all the coefficients here. So we'd go to 2 to 13 to 8 and to 10. And so then our count here would be 16 plus 10. So 16 plus 10 is 26 O's, and then we'd have 26 O's on this side of the reaction here. So this would be balanced with a 2, 13, 8, and a 10. So write and balance the reaction for the formation of Al2O3 from aluminum and O2. And so this balanced reaction would be Al plus O2. Let me save some room here. So aluminum solid, O2 gas to form Al2O3. So let's look at the oxygen first. I'm going to need a 2 here to get this to an even number. And so that's going to need 3 O2s. Otherwise, I'd have a fraction in front of O2. And then 4 ALs. So whenever we combine two or more reactants into a single product, even if there's multiple coefficients of that single product, we call that a combination reaction. So this is a combination reaction. If you flip the reaction, that would be decomposition. If you have one single compound turning into two or more substances, then that would be decomposition, and then our reaction above is the combustion. What is the percent sodium in sodium carbonate? The percent sodium, I should probably add this by mass, just to be clear that that's what we mean. And so we'd be taking 2 times the mass of sodium from the periodic table, which would be 22.99 AMU. We're going to divide by the formula weight of the compound, which we're going to have to work out, but that's going to be 22.99 times 2 plus 12.01 plus 16 times 3. So the formula weight of the compound is about 105.99 grams. So the percent sodium is the 2 sodiums times the mass of sodium. So 2 times 22.99 divided by that formula mass. We need to multiply this by 100%. And that gives me 43.38%. Call that 43.4%. So to 3 significant figures, compare and contrast the mass of 1 molecule of CO2 in atomic mass units. And so 1 molecule of CO2 in AMU is just, taking 12.01 AMU plus 16.00 AMU times 2 for oxygen. And so there'll be 44.01 atomic mass units. So that's the mass of 1 molecule of CO2 in atomic mass units. The mass of 1 mole of CO2 in grams per mole. This is also pretty easy. This is just then saying, well, that an atomic mass would be 12.01 AMU per atom, or it's going to be 12.01 grams per mole of carbon plus 16.00 grams per mole times the 2 moles of oxygen in the reaction. So that gives us a molar mass of 44.01 grams per mole. So grams per mole are numerically equivalent for any molecule to its atomic weight in AMU. So the mass of the molecule in AMU is equal in number to the numerical value of the grams per mole. Now another way we can think through some of the arithmetic here would be if we want to go from AMU, let me do this up here. So if we're going from 44.01 AMU and converting to grams per mole, well, we mentioned this conversion factor before, but there's 6.022 times 10 to the 23 AMU in a gram. There's an Avogadro's number of AMU in a gram. And then this is the mass of 1 single molecule of CO2. And there's 6.022 times 10 to the 23 CO2 molecules in a mole. And so we're dividing by the number, we're multiplying by the same number, so that cancels itself out. And so that's us going from AMU to grams per mole. So that's just another way of seeing how AMU and grams per mole are numerically equivalent for any given substance. Now, what's the mass of 1 molecule of CO2 in grams, though? If you said, well, how much does 1 single molecule weigh? Well, here we'd just be taking the number of grams equal to 44.01 AMU, and we can just use that AMU to gram conversion. This conversion would be given if you ever need it. Sometimes you see 1 divided by 6.022, so sometimes you see the conversion factor that's given that's there's 1.6605 times 10 to the minus 24 grams in 1 AMU, but somehow you can be given this conversion factor or the opposite conversion factor for the number of grams per 1 AMU to make this conversion. But this is a really straightforward problem, just 44.01 divided by Avogadro's number. gives us a mass of 7.31 times 10 to the minus 23 grams. So a molecule can have a mass in AMU. That's a convenient unit to work with if we're dealing with single molecules, because a single molecule has a really tiny mass. So a really tiny mass might be easier to express as AMU. The actual number of grams is really small, but if we're working with large quantities, we might find using the molar mass, the grams per mole, to be a more useful quantity. Okay, so now how do we go from percent by mass data to a formula? Well, the best formula we can get is empirical formula. We're not going to get the molecular formula from this information. We're just going to get the simplest ratio of these elements in our compound. So the way we kind of can relate this problem here is if we have a relationship by mass, we should be able to come up with the ratio of moles of those elements within the sample. So we're going to go from our gram ratio to a mole ratio and then try to get some whole number ratios out of that. And so what we're going to do is start with our 34.6 grams of copper. That's in ratio. I like to think that this is just a ratio to however much mass of iron there is. And that's also in ratio to the mass of sulfur. And so we got to keep these ratios intact. We can do that when we convert to moles just using each of their own molar masses. So the molar mass of copper is 63.546 grams per mole. Okay, then we can convert iron using its molar mass. It's 55.845. And then 32.06 grams per mole of sulfur. And so now when we get our ratios out here, these will be the ratios for the atoms in our the elements in this compound. So 34.6 divided by 63.546. That's 0.5445 moles of copper. Now that's in ratio to 30.4 divided by 55.85. I think technically it was 55.845. 30.4 divided by 55.845 works out to about the same number. In ratio then to 34.9 divided by 32.06 to 1.09, 1.089. And so now if I want to get the whole number ratio, what we want to do is find just some way of getting the whole number multiples here. So if I'm going to divide one of these by a number to keep the ratios intact, I have to divide them all by the same number. So I'm going to divide all these by the smallest. That's a good way to start to try to find the simplest whole number ratio. Well, I guess technically it's 544, but you can see these are both going to be 1. So that gives me 1 mole of copper in ratio to 1 mole of iron. And then 1.089. So pretty clear that it's going to come out to 2. Just to double check. Yep, that comes out to 2. So we get 1 mole of copper to 1 mole of iron to 2 moles of sulfur as our ratio. So Cu, Fe, S2 would be our empirical formula, simplest ratio of those elements. And then for our final example, we have a compound with an empirical formula that's known to be C3H4O. This could have come from %C, %H, %O data, perhaps, and it's found to have a molecular weight of 336.4 AMU. What's the molecular formula? For a molecule, the molecular formula is probably what you really want to know. That tells you more about the compound than the empirical formula does. So let's calculate our empirical formula mass. So it's 12.01 times 3 plus 1.008 times 4 plus 16. That's 56.06 AMU. And so we're going to take the formula weight and we're going to divide by the empirical formula weight. And this will give us a number of multiples of that empirical formula in the overall formula of the compound. So I go 336.4 AMU, divide by 56.06 AMU. This should give me a whole number. If not, we've mistaken our math somewhere. And I get 6. Okay, and so then I have 6 multiples of C3H4O. So I need to multiply each of these by 6. So that's going to give me C18H24O6. Right there. All right, so I'll do it for this activity.